Welcome to Hitex and to today's webinar, miniHIL Test Automation for Motor Control Systems with Thomas Schütz from Protoss. My name is Wolfgang Fuller. I'm working at Hitex Marketing in Karlsruhe, Germany. Hitex was founded in 1976 as a system house and is now a requested tool partner and service provider for training and consulting, testing services, as well as development and production services. Hitex supports you in all phases of your project, from the idea to the finished system.
Yeah, who is Protoss and who am I? Protoss is a company. We provide software tools, test tools, and software architecture for embedded systems. So that's what we do. And who am I? My name is Thomas Schütz. I'm an aerospace engineer who likes embedded software architecture, tests, and tools. And I'm the CEO of Protoss. And yeah, today we are going to talk about motor control systems, how to test them efficiently. So why do we want to do what we do? One very important topic is to test early. The earlier you test, the less effort you have during the testing. So what we try to do is to bring the integration test and the system test to the desktop of the developer or to a continuous integration server, so that it feels more or less like a unit test instead of a real system test. So we need to learn and test earlier. Let's have a look at the development testing gap that exists in most embedded development processes. So from the left to the right, you see the development process for an embedded system. In a typical project, you start with the evaluation board. You develop your drivers, you configure your drivers, then you create hardware-related software components, such as a motor control, battery control, bus system protocols, low-level protocols, and so on. And on top, you have your software components. You integrate everything to an application. And then eventually the hardware is done and you go to a real ECU, to the real hardware, and you integrate this with your real hardware. Usually those systems are tested in those three spots. So in the early phases, mostly with unit tests. The problem with unit tests is you can only test software components. It's really hard to write a unit test with hardware involved. For various reasons, it's just not designed for that. But please continue doing unit tests if you do them. They are a very cheap, very inexpensive way to test a lot of things. So please continue doing that. And later in the process, in many cases, very much later, you have a HIL system test or a real system test. The problem with those tests is that they're very late in the process, so it does not really help you while you're developing your application software. So what we do, we focus on the integration test, and with the integration test, we have the ability to really test early all the aspects of your software integrated in your chip. So that's a very nice and fast way to test your application software in your microcontroller. So why do I want this, and what do I really want and need? I would like to test every code change of every developer within minutes instead of weeks. I want to run full regression tests also for unrelated code. Probably you know, saying, but I didn't change anything there. Yes, you didn't, but still there's a problem, because we all know software has side effects, especially in embedded systems. So we always want to run a full set of regression tests on every change. Then usually I would like to have full test automation to enforce tests, for example, by using continuous integration. So every commit triggers a test and a test run. And in the end, I also need automated hardware in the loop tests to test more than pure software units. because it's an embedded system. So I want to test it integrated with the hardware. Why is it so hard to automate tests for embedded systems? I'll give you an example, a motor control system for an oil pump. It's an actually customer project. What the problem was here, we needed to test the temperature shutdown for all border values for all 300 relevant system states. It's a safety critical system, so we need to test them. What they had before was a climate chamber test setup. So they put the ECU with a complete system, with all the sensors, with power electronics, with the motor, with the pump, with the hydraulic system, with the oil, and so on in the climate chamber. And then they started to run test cases on that by changing the temperature in the climate chamber, which is very, very slow. So it's a big system, so the system is really slow. The full test for all relevant states would have taken something like 30 days. So this was never executed completely, and it also was not really automatable because the hydraulic system failed or the oil was dry or whatever. So there's always been a reason why it could not run automatically. What we did is we took out the microcontroller with the motor control software and all the drivers, and we tested the complete software as a HIL integration test by stimulating only the drivers, so at the pin on signal level, the PWMs and so on, and the temperature sensors. And this gave us the possibility to completely manipulate the environment because it's only a simulation. And we could run all the test cases, the necessary test cases, within 50 minutes. And this runs virtually on every commit, on every change now. So why do we want the hardware-software integration test? You want to test what is changed most frequently, and that's your software. So you will not change the hardware every minute or every hour, but you will change your software while you're developing very, very fast. Then you can test with such a setup, you can test the happy path and the unhappy path, so all the errors you want to test by simulation and failure injection. That's really hard to do with a hardware system because you actually need to destroy the motor or the sensor or whatever. You can test highly concurrent systems, unlike unit tests. So a unit test is not really well suited to test concurrent systems, but our embedded systems are concurrent systems. Then you can completely automate the test execution because it's only a simulation environment and not a hardware environment. You can run the regression tests for every change. So virtually every little change you make, you can run the regression tests completely. And the automated tests are very important for changes, refactoring, and product maintenance. So whatever you want to change, you need a safety net. And those automated tests are the safety net for the developer. So what can you do with such a hardware-software integration test? You can put your system basically in almost any state to test it. By doing change the simulation or do failure injection. And an example would be, for example, positioning if you run against a block for reference run, or the change of torque, or the pump, what happens if it runs dry, or the viscosity changes due to temperature changes and things like that, or also things like temperature limit tests, overcurrents, shutdown path tests, and so on and so on. So those are all typical situations you want to test, and that's not the happy path usually. So let's go to the heart of your application, the motor control itself. So the motor control, in this case, a BLDC motor control, we need to simulate the motor in order to bring the system into a state where you actually can run your test cases or or it even does not start up your system if there's no motor attached. So we need to simulate the motor, and this gives us a lot of possibilities now. Let's have a look at the typical structure for a motor control test setup. On the right side, you see the system under test, so your motor controller application. On the left side, the test system with a plant simulation or other simulations and the test cases. So the system under test provides motor control signals, for example, PWMs. Then the motor plant simulation is executed. It generates a new, for example, a new RPM or a new position or whatever it is you want to simulate. And then it simulates the motor sensor signals so that the motor controller can really run completely without an attached motor. And then, of course, you have other actuators, other sensors, temperature sensors, and position and things like that. Usually you also have bus systems, a CAN, a LIN bus, or other low-level bus systems like SPI or I2C. So instead of the real system, the motor control application controls a simulated environment, a simulated system, including the motor we provide as a plant simulation. Typical examples, a BLDC motor, for example. Here the plant model usually has to be executed with between 15 and 30 kilohertz. You have 3 PWMs in this example, 3 Hall sensors, and so on. And the model speed here is an analog value just for visualization purposes, to understand the model better. Then second example would be a field-oriented control. Here you see if you have a field-oriented control, it's highly probable that you recognize the curves here. And we can run single, double, triple shunt simulations. For the single shunt, we have multiplexing, analog multiplexing included with below 1 microsecond. That's very fast, so that cannot be done in software, but the rest is completely software simulation. The plant simulation also between 15 and 30 kilohertz typically. So the third example would be a simulation for a DC motor with a spring reset. In one direction, you control the motor over a PWM signal, and in the other direction, in this case, we have a position sensor with an analog signal, could also be a digital signal, and the simulation calculates the speed, the spring force, and so on, the position. So how do we do that? Our motto is keep it as simple as possible. With the miniHIL hardware platform, we have a very simple test setup, integration test setup. On the right side, you see the system under test. That's the microcontroller, in this case an ST microelectronics microcontroller STM32, which runs in a pump or in a drilling machine or in a medical device, in a pump for blood or whatever it is. And what we do is now we connect the pins of the microcontroller with over this patch panel with the test system, directly or indirectly. And by doing that, we can run here all the needed environment simulation, the bus protocols and the test cases and so on the test system. It's hard real time because for a motor control, we need hard real time. And in this case, this STM32 it's a Cortex M4 processor, typical for microcontroller for medical devices, motor controls, in industrial applications, or even in motor controls for automotive or avionics. So if you want to simulate and run test cases, you also need to develop the simulation and the test cases. Therefore, we do have a model-based development environment. It's a component-based approach based on the language ROOM, real-time object-oriented modeling. You model the structure and the behavior of the environment simulation and of the test system, also the test cases, and from there you generate the code as C code. You compile it, you flash it to the test system, you run it, and then you get a report as usually as diagrams. We also have a text logging, of course, and when you get the report, you see exactly where an error happens, and you can learn and iterate. That's a very short cycle. It's usually runs within minutes or so. So what's the typical response time for the different test levels? Let's start with a component test. That's a unit test, for example, for your ECU. Here, usually you have execution times in the range of minutes. So that's a typical unit test. Integration test usually is not done. So at least the hardware-software integration test is not done. Then a system test, in many cases, really is run every month or every 2 or 3, 4, 5, 6 weeks. In some cases, if it's a lot of effort, it's executed every 3 months. And that's very slow if you want to detect and retest errors. The acceptance test usually is a system test, so it also takes the same amount of time. What we do is now we introduce the integration test, where we already test a lot of system things here with a miniHIL. In this case, you see an Oryx processor of Infineon on top of the miniHIL board. So that's our system we're testing. And this allows us to have a very fast turnaround cycle within minutes instead of weeks or months. So so the speed is the message here. That you can see the test setup for hardware in the loop test on your desktop. So you have a laptop, for example, or a desktop computer, and right next to it you have the miniHIL, and that's the typical setup for one project or for the developer of the test case that actually can really run it on desktop. That's also the same setup I have here. So just to show you that, here I have the miniHIL board, and I'll do a little live demo after the presentation. The second kind of setup is a test automation with continuous integration. That's what you use for many projects or more than one developer. So not everybody has to run the miniHIL on his desktop. The idea is that on every code change by every developer, so every code change triggers the continuous integration. The continuous integration server then builds and tests and delivers the software potentially, and you get a feedback within minutes. So you get an email if you check something in and it does not test correctly, you get an email. And here you see a typical test setup for 8 projects. Actually, that's our test setup in the rack, in the 19-inch rack with 8 projects. That's a setup where we test our own miniHIL, so hardware and software. And in a typical customer setup, this would look exactly the same, but would have, for example, one board for every project, and that's small, that's inexpensive hardware setup. So it can actually wait until somebody commits, and then it runs within minutes. That's the idea here. So for every code change of every developer, the test is executed automatically within minutes. So now I'm going to run a little demo, live demo. I have prepared a little test setup with a microcontroller. It's actually an STM32 microcontroller, and with a BLDC motor controller. So it generates 3 PWMs. And then in the test system, the PWMs are measured. The new speed is calculated, and according to the new speed, we generate 3 Hall signals as digital outputs. so the microcontroller can actually really control the simulated motor. We also have a temperature sensor to demonstrate the temperature shutdown or warning, limp home functionality or something like that. And then we have a UART to control the speed of the model or of the application, and also for change of direction or to brake the engine and so on. In electrical, on the electrical level, on the signal level, I can show you a typical signal log for such a test run. In this case, with a Celea logic analyzer. Here you see zoomed out the three PWMs and the Hall signals, and here it's the UART control for the speed. If you have a look at the test run, I can show you what this looks like. For example, we change the speed, and then we watch whether it actually really changes. So we can ask the simulation whether the speed is correct or not. Then another test would be we hit a temperature error by running over or under the limit, the temperature limit. And here you see the model speed really goes to 0. The PWM shuts off and the motor gets slower here. And then here we have a warning. We hit the warning temperature. So that's the temperature here, and that's the motor speed. So if the temperature gets below the warning temperature, we expect the system to get slower, to have a limp home functionality. And the last test case would be here the test for motor start if you reach a recovery temperature. So for example, if the temperature gets in the good range again, the motor recovers and continues its work. So those would be typical use cases for a motor control system. So now I'm going to jump into the development environment. As I said before, I have a little miniHIL board here, and I have the development environment, and I'm going to show you how we develop the software on the test system. So we are talking about this processor here. Here we run the environment simulation and all the test cases. So that's the software system in our modeling environment. Here below we have the I/O, so analog adapters, digital adapters, UART. Then we have the duty capture for the 3 PWMs. So if the 3 PWMs are measured every, I don't know, 10,000 times a second or 15,000 times a second, we feed it into the motor simulation. The motor simulation calculates the new speed, and over the whole gen out port, it sends it to the whole generator, and this one here generates the 3 digital signals for the whole sensors actually. So that's the hardware layer. And here in the simulation, in this case, we have basically 2 simulation elements. That's the motor simulation and the motor temperature that converts an analog value 3 point something volt into a temperature in Celsius. So for example, 10 degrees Celsius or something like that. And so the other way around, so we set the temperature here. And in order to do that, we need behavior. So there are various ways to really implement the behavior. The integrated functionality here is a state machine. So you can really model the state machine. So if you get a PWM, new duty cycle measurement from the PWM port, we remember the duty, then we loop back to the start here. Here in the entry code of this state, we calculate the current speed, and then we set over the whole GAN out port, we set the new speed to the component that can generate the sensors. So if I want to see what else I could do. I could change the speed, I could change the direction. And for example, by setting a wrong speed now, I could actually do failure injection. So for example, the motor is not fast enough. So what does my application do on that? So does it create the right error condition and does it shut down? Or also could change the direction just to see whether my application finds out. So those are typical examples for failure injection here. In this case, that's a state-based motor control system. We can, instead of integrating the state machine, we can also, for example, if you're working with MATLAB Simulink, we could also integrate the generated code of a Simulink plant model. That's also very regular use case for us. So now we have the simulation, and the last thing that's missing are the test cases. So let's have a look at the test cases. This actor here, this component, has a interface to the motor simulator, to the UART, and to the motor temperature. So that's what we use for those test cases. I open the behavior, but instead of getting a state machine, I get a test case. So in this test case, I can use all the interfaces I have defined in the on the structural model level, and then I can start to define test steps. For example, I want to set the direction. So what do I do over the UART? I can set the direction. I can request a certain speed and so on. So that's the UART channel. And what do I expect? I expect a send done, and that I actually get from the target the information whether it has worked or not. So one level above, we can build based on those steps. We can build sequences. So for example, we can activate the motor control, set the direction on and so on, off and so on. And here you see what really happens in the system. We have we generate a flat diagram for the sequence diagram for the test case specification. So that's exactly what I have here. If I change this here, you can see that the sequence diagram here also changes. So you have always actual documentation that's always true. So that's what you expect. So in the end, what you want to do is now you want to generate test cases from that and the complete system. So you can hit the button here, and I already did that. And we can connect with this graphical user interface here. We connect with the test system. So for example, I connect with the system. You see the LED green here, LED blue, LED red. So but that's not the interesting thing. The interesting thing is here on the left side. I can run the tests now. So the tests are executed really over those cables, PWM sensors and so on, all simulated. Also the combinatorial test cases we have here. And to show you that it's not fake, I'm pulling a plug. So I guess that's a serial interface. I run the tests, and in the middle of the tests, I pull the serial interface here. So of course, the error is detected. And now I fixed it again, and I can see, for example, that the motor control speed failed in the integration test. So now I know what actually failed in the integration test, but I don't know why. So let's go back to the log of the system of the test execution, so the traces. Let's have a look at the demo integration tests here. I open it in a regular browser. That's just a regular browser here. And here I see where it failed. It failed exactly in this step. And I click. And when I go back to my development environment, I see exactly where it failed. So required speed, request speed, and that's request speed here. And here in this reaction block, it failed because it hit the timeout. So that's how we run it, how you run it on a desktop. And now I want to show you what happens if I change something and I want to execute it automatically. So for that, I have a local Git repository here on my computer, and I also have a local installation of a Jenkins server. Could be any kind of automation server, of continuous integration server, with access to a USB port. It could be a runner for GitLab, GitHub, or Azure, or Azure, or whatever it is. So this job here monitors my repository. And what I'm going to do now, I'm going to make a little sabotage. I will open the motor control, which is also in the same project here. So not in the same project, in the same environment. So the system under test is I'm doing in the same development environment, and I'm looking for a duty cycle because I wanna change the duty cycle. So let's make the duty cycle constant to 20%. Of course, I know that's an error. Yeah? I commit the error. I commit it now to the Git repository and have a look at the continuous integration server, and it immediately starts to execute the continuous integration. So now it starts to build the project, and here you can see it actually flashes the system under test. Now you've seen the blinking here. It really flashes the system under test. It really flashes the test system, and then it executes the tests. That's just the text logging here. And in the end, I can show you the results here on the continuous integration server. So now we see 3 tests failed. Yeah, in the text logging, that's nice, but I want to have a look at it here in my statistics. I click on the last test run. It's yellow, so it did build, but it did not correctly execute all the test cases. Here you see all the test cases that failed in the integration test. So let's have a look at the integration test trace. Again, exactly the same log as I had before on my local machine. That's on the server this time. And if I click on the generated log, and if I have opened the right project in my development environment, it opens exactly the place where the test case actually failed. So a last thing about the reporting, we also have a feature report here, or just a second, feature report or requirement coverage report. In this case, you see 3 tests failed, and here you see 3 requirements failed, and that's the test case that's actually failed for this requirement. It's really nice to know which requirements or which features are covered by which tests, so you can make an impact analysis for your changes, for example. And last but not least, we also generate the complete documentation. So for example, all the test cases are really documented as graphs here. That's much easier for you to discuss them in the team, or also for certification or so. It's easier to for the certifier or for the reviewer to see what is actually expected. Here we have combinatorial test cases, but that's another story. Good. I guess that was it so far. Thanks for your attention, and if you have any questions, feel free to contact us. Michael Weiss for Hitex, or me directly for Protoss. Tell us your testing problems, and we can discuss whether we can find a good solution for you or not.